Hello APC Mechanics students, in Unit 2 Newton's Laws of Motion, Class 12 Circular Motion, Part 1. Section 1 Kinematics of Circular Motion. Now we're gonna do comparison between Cartesian coordinates and polar coordinates, because we know that whenever we have circular motion we're talking about symmetry in which the radius we consider to be constant. And the Cartesian coordinates is being described by the position xy, and the polar coordinates position r theta. R is the radius, theta is the angle, and they are linked together via axis r cosine theta plus a, y is r sine theta plus b, where a and b are the center of the circle. The velocity given by vx, vy is characterized by the speed given by the Pythagorean sum. In the Cartesian coordinate, in the polar coordinates, we talk about angular velocity omega. Both are linked together via the formula v is r omega. Acceleration is given by ax and ay. The magnitude is a radical ax square plus ay square. The polar coordinates, we talk about something which is the angular acceleration alpha. However, these two cannot be directly easily linked. Acceleration ax, ay can hardly be linked to polar coordinates. For this reason, we introduce a new basis in which we will represent the acceleration given by AC, AT. AC is the centripetal acceleration, AT is the tangential one. And remember that acceleration is due to velocity. Velocity is a vector quantity having both direction and magnitude. Whenever the direction varies, this would yield a centripetal acceleration. Whenever the magnitude varies, that would yield a tangential acceleration. And in this case, in this new representation given by the centripetal and the acceleration, the centripetal acceleration is given by v square over r, which is directly linked to the polar coordinates given by the radius. And the tangential acceleration is given by r multiplied by alpha, which is directly linked to polar coordinates. So basically we move on from Cartesian representation to polar representation in order for the linkage between acceleration given by AC and AT to be explicitly linked to polar coordinates. Now the acceleration which is given by ax and ay, which can be also given by AC and AT. Now here pay attention. Either we write the acceleration as ax plus ay or AC plus AT, so we don't mix between them. So we cannot write, for example, the magnitude of the acceleration to be ax square plus AC square. So we either represent the acceleration being in the Cartesian or the polar set, and the magnitude is given by radical ax square plus ay square, which is also equal to radical AC square plus AT square. So basically this is the map between the Cartesian and the polar coordinates for circular motion. Velocity and angular velocity. So suppose here we have circular motion in which the object represented by a dot has an angular position theta moving by radius r. S would be the actual distance, the measure of the distance, which is the arc, as it moves starting from this point A to the point B. So if you cut the circle here and stretch this arc, it would be represented by length by a horizontal line like this. The measure of this in meters is equal to this arc S. The arc length S is related to the polar coordinates r theta by S is r theta, so this is a new equation that we should consider. Theta, omega and alpha are related via derivatives. So remember that x, v and a are related via derivatives. If we derive x, we would get the velocity. If we derive the velocity, we would get the acceleration, and here we can do something similar. So omega would be represented by d theta divided by dt, and alpha would be represented by d omega by dt. Remember that this is not w, this is omega. Then let me write here the map. We have theta, which is the angular position, omega the angular velocity, alpha is the angular acceleration. By deriving theta we get omega. By deriving omega we get alpha. In other words, omega is d theta by dt and alpha is d omega by dt. Now if we derive both sides with respect to time, so I will consider this equation and derive on both sides. So that would be d by dt of s, d by dt of r theta r is a constant, can be dragged out. Now what does ds by dt represent? So as we've mentioned that s is the measure of the distance or position along the arc, then ds by dt would give us the linear speed v along which the point is moving along the circle. And from this definition, d theta by dt would be omega. So basically this is a new equation, v is r omega, that we have presented previously, which is the relation that we have introduced previously. V is the linear speed of a specified point on the disk. Omega is the angular velocity, which represents how fast an object is rotating. So let's consider the following animation, which is gears moving. Now because these two gears are connected to each other, they're moving, so they have the same linear speed. So if you consider a point here A on the rim of the disk and a point B here moving at the rim of the disk, so both points A and B have the same linear speed. However, they have different angular velocity omega. What does angular velocity omega represent? It represents how fast an object is rotating. And if you look carefully, the red gear is moving faster than the green gear, which means omega for this red is greater than the omega for the green. And similar argumentations can be done for the second animation. Both of them have the same linear speed because they are connected by this, but different angular velocities. As you can see that the smaller gear is rotating faster than the larger gear, which means omega for this gear, small, is greater than omega of large. And for the final animation where we have a disk, all points on the disk, so if you consider 2 points here, A and B, they are rotating at the same angular speed omega, because omega represents how fast an object is rotating. So both points A and B on the disk for different radii have the same angular speed. But what would be the difference? If you consider here 2 points A at the rim of the disk and B another point here, so we say that omega A is equal to omega B, because all points of the disk admit the same angular speed omega or angular velocity. However, if you multiply this by the radius RA and this by the radius RB, because RA is greater than RB, which makes this greater than that, and we know that R multiplied by omega, this is VA, and RB multiplied by omega B, this is VB, then points away from the center of the disk would have a linear speed greater than points closer to the center of the disk, because they are at a greater radius. All points on the disk have the same angular velocity or the angular speed. However, when you start getting away from the center of the disk toward the rim, your linear speed changes, because the linear speed is the product of the radius times the angular velocity, which is constant for all points of the disk. Section 3, centripetal force. Objects in circular motion admits centripetal and tangential accelerations. The centripetal acceleration, as we have said previously, is due to the variation of the direction of the velocity. Tangential acceleration is due to the variation of the magnitude of the velocity, because velocity has both direction and magnitude. Centripetal acceleration, as a definition, is given by v squared over r. This can be determined via calculus. Always exists in circular motion due to the continuous change of direction of the velocity, as the velocity is tangent to the circular trajectory. So whenever we're talking about circular motion, we cannot neglect acceleration. We always have acceleration, and this is coming from the fact that if you consider this animation back again, so okay, it's not being repeated. Now let me consider 2 points here. This is the point A, this is the point B. The velocity here would be to the left, the velocity here would be to the right, which means that the velocity at each point of the disk or the circular motion is changing, which means the direction of the velocity is changing, which means that always along circular motion we have centripetal acceleration. So always exists in circular motion due to the continuous change of the direction of the velocity, as the velocity is tangent to the circular trajectory. The centripetal force, so if we have acceleration, how can we get the force? Simply we multiply it by the mass, mv square over r, would be understood as the required magnitude of the unbalanced forces along the center to keep an object of mass m in a circular path of radius r. And this definition for the centripetal force is very important. So we should understand that in order to have circular motion, we should require a magnitude given by mv square over r, which represent the magnitude of the unbalanced forces along the center that is required to keep an object of mass m in a circular path of radius r. Notes and misconceptions. The centripetal force Fc is not a force. So basically this is not a force. This is the magnitude, the required magnitude of the unbalanced forces along the center to have a circular motion. For this reason, we don't ever represent it in an FVD. The centripetal force Fc is not a force again, but rather the direction of the forces acting inward along the center. So the direction of the centripetal force would be the direction of the forces acting inward along the center. In circular motion, several forces might be acting on the object. If the motion is uniform circular motion, which means it's a constant speed, then the net force is said to be only the centripetal force must have a direction only toward the center, and we will discuss this more and more later in the coming videos. Now let me consider here a car moving. So this is a top view in which a car is moving along this circular path, and let's suppose that the speed is constant or independent whether the speed is constant or no. Here we are only interested in representing the centripetal acceleration and the velocity. So because the car at point A is moving toward the right at this specific moment, the velocity is tangent to the trajectory and the centripetal acceleration is toward the center. I'm not claiming that the car is moving at a constant speed, so I'm not claiming that there is no tangential acceleration. We don't know if the car is speeding or slowing down, speeding up or slowing down. I'm just saying that we have centripetal acceleration due to the circular motion, and in this case is toward the center. So now at the point B, which is here, so the velocity would be down, tangent to the trajectory, and the centripetal acceleration would be toward the center. Similarly, for the point C, which is here, velocity would be up. Sorry, for the point C, which is here, velocity would be left, acceleration would be up. Similarly, for the point D, which is here, acceleration would be, velocity would be up, acceleration would be toward the center. Example 1, a person is riding a distance r from the center of a rotating platform as shown in figure 1. The person is moving with a constant linear speed v. For the view looking down on the person in figure 2, which of the following best shows the direction of the net force exerted by the platform on the person? So because the person is rotating at a constant linear speed, which means the net force should be pointing toward the center, which makes B the correct choice. Now section 4, rotating disk. A block of mass m is placed on a disk rotating at a constant speed v, which means that the net force should be pointing toward the center. The aim of this section is to determine the maximum distance from the center at which we can place the block and doesn't slip. So here, if this disk is rotating at an enough speed that makes the block slip, so if you consider different points at different distances from the center, this is A, B, C, and D. As we start moving the block away from the center, we expect that at some point at the edge of slipping, the block will start losing contact, it start to slip, and it will slip away from the disk. The aim of this section is to determine the maximum distance, so the maximum radius from the center at which we can place the block and doesn't slip. And by maximum, it means we are at the verge of motion. And we know that why this is important, because the friction would be replaced, the static friction would be replaced by mu s Fn. The block can be placed at specific points on the disk without slipping out of the rim. Here we assume the direction of tendency of the slipping is away from the center. Okay. The disk or the block might have several directions of slipping. For example, slipping like this, slipping like this. Here we're assuming that the direction of slipping is just away from the center, radially outward. Now suppose we place the block at a point such that it doesn't slip and moves with the same speed of the disk. So the block is in direct contact with the disk and it doesn't slip. As the disk rotates with an angular velocity omega, the block will rotate with an angular velocity omega as well. What are the forces acting on the disk? We know that it's important to do an FBD because later we're gonna utilize that using Newton's second law. We have the pull of gravity, we have the normal push which is up, and notice that I have represented them to be balanced forces because there's no vertical upward or downward motion, and because the tendency of motion is away from the center, then the friction would be toward the center, and this is a static friction. Although the block is rotating, but why it's a static friction? Because there is no relative motion between the block and the disk. They are rotating as a one body. So this friction is a static friction and not kinetic friction. Alright? When do we have kinetic friction? When there is relative motion between the block and the disk. The static friction has a direction toward the center, then the force that causes the circular motion is the static friction. So here we can ask ourselves, what is the force that is responsible for the circular motion? It's the static friction because it's pointing toward the center. Then this force should be equated by mv square over r, because this is the magnitude required to achieve a circular motion through a radius r and a speed v. We say that the static friction is the centripetal force and should be equal to mv square over r, which is the magnitude required to keep the block in this motion. Then the static friction, okay. Now along the vertical we would say that Fn is Fg, they are balanced forces, which means the normal push is mg. Now along the center, so what does this direction represent? This is not a horizontal direction, this is the direction toward the center. We have that friction would be equal to mv square over r. So this is the magnitude of the required force to keep the object in a circular motion. So usually we're gonna say that F naught is ma. Because we're considering the centripetal direction, then that would be C. What are the forces acting along the center? We have the friction, and A would be represented by V square over R. So basically this is coming again from Newton's second law. By utilizing the centripetal direction, that would be C, and AC would be replaced by V square over R. We cannot use directly friction is mu s Fn because we don't know if you are in the case of the edge of the slipping. But remember that the aim of this section was to determine the maximum radius in which we can place the block and it doesn't slip. Suppose the block is moved away from the center till we reach the stage of the edge of the slipping or the verge of motion. Now we can safely use that friction is mu s Fn. And we know that the normal push in this case can be replaced by mg, and we're searching for the value of r. M and M in this case they cancel, and isolating for r, then r is given by v squared divided by mu s multiplied by g. Then the maximum radius r in which we can place the block without slipping is given by r is v squared divided by mu s g. If the speed of the disk increases, this requires more static friction to keep the block attached to the disk. And this is because as the speed v increases, then the required magnitude mv square over r to keep the block in circular motion would increase. So here what I'm saying is that if we have a disk and we're placing the block at a specific radius, and if we start increasing the angular speed of the disk, which means speed v increases, as the speed of the disk increases, then this term would increase, which means that the required static friction, the required magnitude of the static friction should be greater in order to compensate for this increase mv square over r. Mv square over r can be expressed as mv square over r. Now v can be replaced by r omega. Now here the power 2 is for both r and omega, that would be r square omega square over r, and that would be mr omega square. If we place the block at a greater distance from the center, radius increases. This requires more static friction to keep the block attached to the disk. And this is because as the radius increases, then the required magnitude mr omega squared to keep the block in circular motion would increase. Let me do the following argumentation, which is super important. What I'm saying here is that as the radius r increases, would this require a greater static friction or less static friction in order to keep the block attached to the disk? Now, referring to this expression, directly one can claim as r increases, then the required force mv square over r decreases, which means that the static friction required to keep the block attached to the disk is smaller, and this is completely wrong. Let me explain why. Because as r increases, also the linear speed increases, because at the beginning of the video when we have the animation of the disk, we said that the linear speed increases as we are moving away from the center. So we cannot use this argumentation in order to justify whether the required force is greater or smaller. What we're gonna do is that v would be replaced by r omega and we would achieve this expression. Why this is important? Because we know that all points along the disk have the same angular speed omega. So m is constant, omega is constant. As you can see that as r increases, then this term, which represents mv square over r, increases, which means briefly, as the radius, as we're putting the block at points away from the center, this means that the required static friction should be greater in order to compensate for the greater force given by mv square over r. For this reason, we determine the maximum radius, that is, we determine the maximum radius, which is the position away, the greatest position away from the center in which we can place the block without slipping. Now, prerequisite knowledge, section 5. Often problems in physics require prerequisite knowledge. Here we introduce some ideas related to circular motion. A block rotated by a spring on a frictionless table. The tension in the spring governed by Hooke's law Tkx causes the centripetal motion and will be equated by mv square over r. Suppose we have the following configuration. The spring has a free length L. We attach a block to the spring and the spring starts to rotate in this horizontal plane. What are the forces acting on the block? At this specific moment, we have the pull of gravity, we have the normal push, we have the force of the spring or the tension force given by Fs. These are balance forces, they cancel. So basically the force which is responsible for the circular motion is given by the force of the spring governed by Hooke's law in the case of a spring given by Ax, and this should be equated by mv square over r along the centripetal direction. Remember that Fs in this case would be given by ma coming from Newton's second law. And if you consider the centripetal direction, that would be c, so Fs, which is kx, would be given by mv square over r. Similarly here, if a block is rotated by string, remember that string is not governed by Hooke's law. It has a fixed radius, it doesn't elongate or compress. On a frictionless table, the tension in the string causes the centripetal motion and will be equated by mv square over r. Similarly here, if you consider this point, it would be the pull of gravity down, the normal push is up, the tension which is toward the center, these will cancel, and basically the tension would be equated by mv square over r. Exercise 1. A car is traveling clockwise around a circular racetrack of radius 1440 meters. When the car is at the northernmost point on the circle as shown above, it has a speed of 36 meters per second and is slowing down at a rate of 1.2 meters per second square. They're asking us about the direction of the velocity of the car independent of the state of motion. The velocity would be always tangent to the trajectory like this, and the correct answer would be due east. A spring has a force constant of 100 newtons per meter and unstretched length of 0.07 meters. One end is attached to a post that is free to rotate in the center of a smooth table as shown in the top view above. The other end is attached to a 1 kg disc moving in uniform circular motion on the table. So this is a top view. The motion is contained on a horizontal plane which stretches the spring by 0.03 meters. Friction is negligible. What is the centripetal force on the disc? So basically this is a top view. A horizontal view would be something like this, or a front view. That would be the spring. and that would be the object. What are the forces acting on the object? We have the pull of gravity, we have the normal push, and we have the tension in the spring, so let me say Fs, along the center. They're asking for the centripetal force on the disk. This can be utilized by Newton's second law. We can say that F naught is ma. And now let's consider the centripetal direction. So along the centripetal direction we have Fs, and that would be mas. So Fs would be given by Hooke's law kx, and basically this would be given by mv square over r, and we know that this is the centripetal force. So the centripetal force that we're searching for is mv square over r. We're searching for that is equal to kx. K is the stiffness of the spring given by 100, and remember that x would represent the elongation of the spring. The unstretched length of the spring is given by 0.07 meters, but we're not interested in this. We're interested in the stretch, which is 0.03. Plugging that on the calculator, we're gonna have 3 newtons, and the correct answer in this case is B. Exercise 3. The maximum mass that can be hung vertically from a string without breaking the string is 10 kilograms. So the maximum tension that the string can handle is given by what? So this is the string and this is the mass. If the maximum mass is 10 kilograms, and what are the forces acting on the string? That would be the pull of gravity, the tension. Then the tension would be equal to the pull of gravity, which is mg, and that would be 10 multiplied by 10. That would be 100 newtons. Why I'm referring to be g given by 10, not 9.81? Because the answers look perfect. So T equals 100 newtons. That would be the maximum tension that the string can handle without breaking. A length of this string that is 2 meters long is used to rotate a 0.5 kg object in a circle on a frictionless table with the string horizontal. So this is a horizontal motion like this. This is a front view, and the string and the mass is rotating in a horizontal circle like this. Then what are the forces acting on this mass? We have the pull of gravity down, we have the normal push from the table, which is up. It is frictionless, we don't have friction, and we have the force of tension toward the center. The maximum speed that the mass can attain under these conditions without the string is breaking is most nearly, so we need to utilize Newton's second law given by F naught is ma. Now what are the different forces acting along the object? We have the pull of gravity, the normal push, the tension in the string is ma. So let me consider the centripetal direction. That would be 0 plus 0. So toward the center is positive. This is ma centripetal, which is T is given by mv square over r. We're searching for the value of v. Then v would be given by the radical of r multiplied by t divided by m, which is basically radical of. Now here, what is the radius? This is a string, so it cannot be stretched, neither elongated or compressed, so the radius would be the same length of the string, which is 2. The tension is maximum, which is 100, divided by the mass, which is 0.5. Plugging this expression on the calculator, that would give us 20 meter per second, which makes D to be the correct answer. Finally, exercise 4, which is an exit ticket for today's video. Let me remind you of a few formulas that we need them here. Omega, which is the angular velocity, can be expressed as 2 pi f, which is expressed as 2 pi over the period, and these are given on the paper sheet. One end of a string is fixed. An object attached to the other end moves in a horizontal plane with uniform circular motion of radius r and frequency f. If the tension in the string is Fs, if both the radius and frequency are doubled, what is the tension is? So we're talking about doubling both the radius and the frequency, so the factor of change. Remember here, the factor of change can be used perfectly, unlike the Atwood machine. In the Atwood machine, the problem was in the numerator and in the denominator, because we have plus and minus, and that would break down the symmetry in the FOC method. Now F naught is ma, The forces and acting on such a system on a horizontal plane, suppose we have a support which is a table, or ignoring even this equation, let me directly proceed to the case where the force which is causing the centripetal motion is Fs, and this should be equated by mv square over r. We're interested in checking how does Fc changes when we double the frequency and the radius. Now the mass is constant, it won't change. We have r explicitly, but the problem is with v, because we know that v is a variable as well. Now let me switch v to be r omega, then that would be m r omega to the power of 2 divided by r. Omega still ain't enough, we need to replace it by 2 pi f, then that would be m r 2 pi f to the power of 2 divided by r. And let me do some mathematics. That would be m r square 4 pi square f square divided by r. This cancels with that, and that would be 4 pi square m f square multiplied by r. Now everything is constant except for f and r. Now we can apply the FOC method. That would be 1 for all of these. Frequency is doubled, r is doubled, and that would give us 8. Then the factor of change is 8. And that's it for me in this video, guys. See you soon in a new one.